Logic Gates by Isaiah Francis. Logic gates are devices that use binary inputs to find an output. The most common types of logic gates are OR, NOR, AND, NAND, and XOR. Logic gates are common in engineering because they provide consistency to devices and systems. Logic gates are commonly measured through truth tables, but can also be measured through Venn diagrams. In a truth table, 2 inputs and 1 output are shown. The 2 most common types of logic gates are yes and not gates. In a yes gate, if the input is off, the output will be off, and if the input is on, the output will be on, just like a light switch. In a not gate, if the input is off, the output will be on, and if the input is on, the output will be off. First, we have an AND gate. An AND gate has 2 or more inputs for a single output. In our schematic, we use an LED to represent our output. In the schematic, voltage passes through the resistor and the LED where it meets the transistors, which can only be turned on if the switches are both on. This truth table shows how an AND gate works. If A is off and B is off, then the output will be off. If A is on and B is off, the output will still be off. If A is off and B is on, it will still be off, but if both A and B are on, the output will be on. This truth table can be proved using logic blocks. If input A and input B are both on, then the output is on. But if one is on and the other isn't, it will turn off. A real-life application of an AND gate would be a door with 2 locks. Each of the 2 locks would act as an input, and the door opening would be the final output. If one of the locks is unlocked but the other is locked, the door will not be able to open. But if both locks are unlocked, the door will be able to open. Next, we have the NAND gate. The NAND gate produces an output when none or only one of the inputs are on. Next, we have the schematic. When neither of the NPN transistors are on, voltage passes through the resistor, turning on the LED. This is also true if only one of the NPN transistors are turned on. To turn the LED off, both NPN transistors must be turned on. When both transistors are turned on, the resistance is lowered, allowing the voltage to travel to the ground, turning off the LED. This can be proved with logic blocks. When both inputs are turned off, the output will be on. If one is off, the output will still be on, but if both inputs are turned on, the output will turn off. A real-life application of a NAND gate would be a security system consisting of a door, window, and alarm. If the door or window is open, the alarm will go off. If both are open, the alarm will also go off. But if neither of the 2 are open, the alarm will not go off. Next, we have the OR gate. In an OR gate, as long as one input is turned on, the Y output will be turned on. This is shown in the truth table. Both inputs are turned off, so the output will be turned off. But in these, as long as one input is turned on, the output will all be on. We can prove this truth table using logic blocks. If one or both inputs are turned on, the output will stay turned on, but if both are turned off, the output will be off. A real-life application of an OR gate would be an iPhone turning on. The inputs would be the home button and motion detection, and the output would be screen activation or the screen turning on. If input A, which is the button, is pressed, the screen will be activated. Or if input B, which is the motion detection, occurs, the screen will also turn on. Or if both happen at the same time, the screen will turn on too. Next, we have the NOR gate. The NOR gate will only produce an output when both A and B inputs are turned off. In the schematic, we can see that voltage will flow through the resistor and LED to the ground, turning the LED on. But if either of the transistors are on, the voltage will be redirected, turning the LED off. In the truth table, we can see that turning both inputs off is the only way we can receive an output. We can prove this truth table using logic blocks. If both inputs are off, the output will be on, but if either of the inputs are turned on, the output will turn off. A real-life application of a NOR gate would be traffic lights. The inputs would be the red and yellow lights, and the output would be the green light. If the red light is on, the green light cannot be off, and if the yellow light is on, the green light can also not be off. But if both lights are off, the green light can be on. Finally, we have the XOR gate, which is a combination of the OR, NAND, and AND gates. In an XOR gate, our A and B inputs go into OR and NAND gates, giving us outputs, which act as inputs for our AND gate, giving us our final output. In our XOR truth table, we can see that an output only occurs when one or the other inputs are turned on. If both inputs are off or both inputs are on, we will receive no output, but if one or the other is on, we will receive an output. This truth table can be proved using logic blocks. Right now, both inputs are off, so there's no output, but if one or the other inputs are turned on, we will receive an output. A real-life application of an XOR gate would be a two-way light system. The inputs would be two light switches and the output would be the lights turning on. If one of the switches turned on and the other is off, the lights will be on. If the other is turned on and the first one is off, the lights will also be on. But if both are on or both are off, the lights will stay off.